Hello chemistry students, welcome back. This is Dr. Tullis and we are going to be covering the structure of atoms and looking at periodic trends. We are picking up where we left off when we were talking about quantum numbers. So this is a bit of a review. We have our quantum number, our N, which is our shell. We have our L, which is our subshell, our ML, which is our orbital, and our MS, which is our spin. No more than 2 electrons can occupy the same orbital, and if there are 2 electrons in the same orbital, they have to have opposite spins. That is the Pauli exclusion principle. No 2 electrons in an atom can have the same 4 quantum numbers. Let's look at an example here. Hydrogen we know has 1 electron, so it is in energy level 1, so its N is equal to 1. Its subshell is S, which is 0. Remember, P is 1, D is 2, F is 3. In the S subshell, there is only 1 orbital, and we call that 0. And since there is 1 electron, it's always going up first. We'll talk more about that later. So it has a plus 1/2. Then if we look at helium, we add a second electron. And Pauli exclusion says if we add a second electron, it has to be in the opposite direction. So we show that as a down arrow. So the first electron is 1, 0, 0 plus 1/2. That second electron, look, it's very similar. 1, 0, 0, but it's a minus 1/2 for that MS. Again, no 2 electrons can have the same set of 4 quantum numbers. By showing our electrons like this, it is called an orbital box diagram. We're going to be doing a lot of those. This is just a review, hopefully, in our energy level 1, our N is equal to 1. We only have S subshells, so therefore there's only 1 orbital. 2 electrons can fit in it. Again, maximum electrons is 2. In our second energy level, we have 2 S's and 2 P's. In our S, we have 1 orbital that can hold 2 electrons. And in our P, we have 3 orbitals that can hold 6 electrons for a total of 8. Then we get to energy level 3. We have 3s, 3p, and then we have 3d. Remember, the 3d is in the 4th row. In 3s, there's 1 orbital, which can hold 2 electrons. P has 3 orbitals that can hold 6 electrons. And D has 5 orbitals that can hold 10 electrons. So 18 total electrons for 3. In 4, we have S, P, D, and F. All the way at the bottom of the periodic table, we have our lanthanide and actinide series. 1, 3, 5, and those ones have 7 orbitals that can hold 14 electrons. The 4th energy level shell can hold 32. What element has the following electron configuration? Well, if we look here, we've got 1s completely full, so that takes out row 1. 2s and 2p, that takes out row 2, so now we're onto the 3rd energy level. We have 3s covered, so that takes out the first 2, and then we jump over and we count 1, 2, 3, 4 electrons. That must be sulfur. We're going to write the electron configuration of atoms. The procedure by which electrons are assigned to orbitals is known as the Aufbau principle. It's a German word that means building up. Electrons in an atom are assigned to shells, which we know are N, subshells L, in order of increasingly higher energy. In this way, the total energy of the atom is as low as possible. So there's 2 rules for filling subshells. Electrons are assigned to subshells in order of increasing N plus L value. What does that mean? I'll show you right here. Energy level 1, and let's say we had our L was 0, which means this is S. L of 1 is P, L of 2 is D, L of 3 is equal to F. So we know in 1, the first row, there's only S's. So 1 plus 0 is 1. And then we move on to 2s. 2 plus 0 is 2. Then we move on to 2p, jump over to the right, and 2p would be 2 plus 1, which is 3. Moving on to energy level 3. We move on to 3s. 3 plus 0 is 3. So notice that those two are both equal to 3. So what do we do there? For two subshells with the same value of n plus L, the first to be assigned is the lower n. So when I have both of these, 2p and 3s of the same value of n plus L, the lower number n. So 2p, 3s. 2 is obviously the lower number, so 2p fills before 3s. Here are some examples to these rules. We assign electrons into 2s before we put them into 2p. We also assign electrons to 2p before we fill 3s because the n for 2p is smaller than the n for 3s. So obviously 2 is smaller than 3. Electrons are assigned to 4s before 3d because, let's look at the n plus L value. 4s is 4 plus 0. 3d is 3 plus 2, which is 5. So 4 is obviously lower than 5. 4s fills before 3d does. This kind of shows us the same situation here. 1s, 1 plus 0 is 1. For 2s, 2 plus 0 is 2. For 2p, 2 plus 1 is 3. So far we're going 1, 2, 3, filling up by energy. 3s, 3 plus 0 is 3. Now notice both of these have the same, but 2p is lower because obviously 2 is lower than 3. 4s orbital has a lower energy than 3d. Again, that just shows what I did mathematically on this slide before. Then we move on to effective nuclear charge. The order of energies for electrons in shells and subshells in an atom can be rationalized by introducing the concept of effective nuclear charge. Z star is the net charge experienced by a particular electron in a multi-electron atom, resulting from a balance of the attractive forces of the nucleus. Remember, we have positive protons in the nucleus. And the repulsive forces of the other electrons. Those are negative. Positive, negative, right? The Z star, or the nuclear charge, increases across a period owing to incomplete screening by inner electrons. That explains why 4s is of lower energy than 3p. So let's look at our Z star. We essentially just take our protons and we subtract the number of inner electrons. Let's look at lithium. Lithium has 3 protons. Its atomic number is 3. And we subtract the inner electrons. So everything that's in row 1, which is 2 electrons. So 3 minus 2 is 1. It has an effective nuclear charge, or a Z star, of 1. Let's look at beryllium. Beryllium has an atomic number 4, so 4 protons. We subtract all the inner electrons. Again, everything from row 1, which is 2. So it has an effective nuclear charge of 2. Boron has 5 protons, so 5 minus everything from row 1, which is 2. So it has a Z star of 3. Let's look at electron configurations. Where electrons are found in the shells, subshells, and orbitals that result in the lowest energy for an isolated atom of the element is an electron configuration. The electron configuration of H, of hydrogen, is written like this, and we read it like this: 1s1, 1s1. That means hydrogen has 1 electron in the S subshell in the first shell. That's it. Helium, we know, helium is right here. It has 2 electrons in the first shell in S's subshell. So we would write it like this: 2 electrons in the first energy level in the S. We would read it as 1s2, 1s2. There are 2 electrons in the S subshell in the first energy level. Now remember, when we are filling orbitals, we have to remember 3 things. Aufbau principle, we always go from lower energy to higher energy. We have a new rule called Hund's rule. Hund's rule says that when we are filling orbitals, each electron is assigned to a different orbital before we double up. And when we fill those each orbitals, they have the same spin as the previous one. I'm going to skip forward to the next slide to bring that home. Let's say I'm filling up my 2p orbital and I have 3 electrons. We know that p has 3 orbitals because they can fit 6 electrons. But if I have 3 electrons, I'm going to go 1, 2, 3. Essentially, think about if you're getting on a school bus and there are some people sitting in seats, but there's some empty seats. People are going to sit in an empty seat before they sit with somebody else. So we would not fill it up like this, 1, 2, 3. No, we don't want to pair up if there's an empty place for that electron to go. So we fill from left to right, and notice that we keep the same spin until we come back and double up. And then, like I said, we have Pauli exclusion principle that says if I do need to put a second electron in that orbital, it needs to have a different spin. And the electron configuration of an atom is the total sum of the electrons from lowest to highest. So here's Pauli. Let's say I need to put 5 electrons in that p sub-level. I'm going to go 1, 2, 3, then double up 4, then double up 5. So these two, when I put them in, they need to have opposite spin. I would not go 1, 2, 3, 4, 5. No, that would not work. If they're in 2 electrons in the same orbital, they have to be opposite spins. And the conventional way to write it is to write up first, and then when you go back, you do down. So up first, then down. Let's look at lithium. Put your finger on lithium on the periodic table. It is in the first column, the first group, in my second row, my second energy level. So we would fill up first my 1s, I would go up, down, and then there would be 1 electron in my 2s. That's it. This is my orbital box diagram. And I would write my electron configuration like this: 1s2, 2s1. And what's really cool, if you add the exponents, this 2 and this 1, 2 plus 1 gives us 3. That's its atomic number. Let's move over to beryllium. Beryllium is in my second row and my second group. So I'm going to fill up my S. To get to beryllium, I have to fill up S, 1s2. And then I'm going to fill up 2s2. And then we're full. And look, we have 4 total electrons. This is my electron configuration. This would be my orbital box diagram. Let's move over one more to boron. Boron, I skip over to group 3 or 13. I'm going to fill up my 1s, I'm going to fill up my 2s, and then I get to 2p. Remember, p has 1, 2, 3 orbitals, so I do have to show those, and I only have 1 electron filling that first orbital. I would write it like this: 1s2, 2s2, 2p1. 2 plus 2 is 4, plus 1 is 5. Again, lower energy to higher energy to even higher energy. Let's look at carbon. Carbon has 6 total electrons. We're going to fill up 1 with 2 electrons, fill up 2, S with 2 electrons, then we get to 2p, and we have 2 electrons in p. It's the second one in the p. So I'm just going to go 1, 2. Moving over to nitrogen. Fill up 1s, so 1s2. Fill up 2s with 2. In P, for 2P, I'm going to have 1, 2, 3. So 1s2, 2s2, 2p3. Add up those superscripts and we should have a total of 7. Let's move over to oxygen. Oxygen has an atomic number of 8. I'm going to fill up 1s, I'm going to fill up 2s, and I get to 2p, and there's 4. Oxygen, if I counted, 1, 2, 3, 4 in the p orbits. So I'm going to go 1, 2, 3, go back, 4. Fluorine has an atomic number of 9. 1s2, 2s2, 2p, if I counted, it's 1 before neon. So it's going to have 1, 2, 3, 4, 5 electrons in that p orbital. Notice that there's 1 more spot to fill up that p orbital, and neon is going to do it. Neon's electron configuration is going to fill up 1s with 2, 2s with 2, and 2p, it's going to fill up that 2p with 6 electrons. Notice that we have reached the end of the second period and the second shell is full. Let's look at the third row. I want to look at aluminum. Aluminum has 13 electrons. So I'm going to start filling up. 1s2, 2s2, 2p6. When I look at aluminum in the third row, it's not in my S. I have to fill up my 3s with 2 electrons before I hop over to the right. And it is the first atom in that p block. So I only have 1 electron in that p orbital. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. Now, as you can imagine, this can get to be quite a mouthful if we, let's say, get further down the periodic table and even just look at silicon. I mean, that last one was a mouthful. There's a shorthand way of doing it called the noble gas notation. Essentially, you take the noble gas that comes before the atom that we're looking for, and we put it in brackets. So that shows me all of the core electrons, and then I just do the outermost electrons. So if I look at silicon, for example, and I did the whole electron configuration, it'd be 1s2, 2s2, 2p6, 3s2, 3p2. So the whole inner core, everything that's not the outermost, my outermost are my 3s here. So my inner electrons are the 1s and the 2s. 1s2, 2s2, 2p6. That is neon. Then I only have to show the outermost electrons, 3s2, 3p2, 1, 2. So that would be my noble gas notation. Here is a whole bunch of electron configurations all the way up to 109. And notice that they are the noble gas electron configurations. Why don't you try? Pause the video here and try to get the electron configuration for sulfur. Show me the spdf notation, which is going S's, then P's, and D's, and F's. Try doing it with the noble gas and draw the orbital box diagram. How did you do? 1s2, 2s2, 2p6, 3s2, 3p4. The noble gas notation, neon, is all of my inner electrons, and then I ended with 3s2, 3p4. The orbital box notation, if you did the whole thing, great. If you did the neon in brackets and then 3s2 filled and 3p4, remember I would go 1, 2, 3, 4. I'm going left to right because of the Aufbau principle. I am doing 1 in each orbital because of Hund's rule. And when I go back to put the 4th one in, it's the opposite spin, which is Pauli exclusion's principle. Pause here and try to figure out these two. Hopefully you got chlorine for this first electron configuration, and check to see if yours matches mine for phosphorus. Pause the video here, see if you can do these two. How did you do here? This one was a tricky one. We did the electron configuration for chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. And when I did this, I wrote in, because I wanted quantum numbers for each of the electrons in that third energy level. So in that third energy level, there's 5, 6, 7 electrons, 7 quantum numbers. It might seem like a lot, but if you were to look at it carefully, my N is going to be 3 for all of them. My L, again, for 3, I'm only looking at these guys. My 3S, I'm going to have 2 of them that are zeros. And all the rest of them are going to be in P's, so they would be 1s. If I look at the ML values, ML, remember, S is 0, and then I have -1, 0, and +1 for my P's. So I'm going to have a -1, 0, +1, which is my -1, 0, +1. And then I went back and I went down, down. So in the -1 and the 0. And then lastly, I'm going to look at my spin. For my S's, I'm going to have +1/2, -1/2. And then I'm going to have +1/2, +1/2, +1/2. And then when I went back for 6 and 7, -1/2, -1/2. And there's your 7 quantum numbers. How about the next one, calcium? The valence electrons of calcium, there are 2 of them, 4s2. And they look like this. So my N is 4, S is L is 0, The only place for them to be in that one orbital is 0. The first one is plus 1/2 and the second one is minus 1/2. Now, it's been all fine and dandy when we've done 1s, 2s, 2p, 3s, 3p, 4s even for calcium. But then we get to the transition metals. And I'm going to hop back to this one diagram where, remember, after 4s comes 3d. And then after 3d, we go back to 4p. So 4, 3, 4. And remember, 4s is a lower energy level than 3d. Remember when we did our addition, our n plus l? So our 4 plus 0 is 4, and our 3 plus 2 is 5. So 4s is lower energy than 3d. That's why we fill 4s than 3d. So if you put your finger on titanium, titanium's noble gas before it is argon. So I would say argon, and then 4s2, and then it's the second element into that transition metal. So I would say 4s2, 3d2. But, so this is how I start. When I'm doing transition metals, I go from left to right. So 4s2, 3d2. But when we write it, so I start off writing it like I just did. That's our electron configuration by filling it up. We fill 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, and that last one was 2. When we write it out, we keep our numbers together. So in this case, argon is 1s2, 2s2, 2p6, 3s2, 3p6. This is argon. Now I need to keep my 3d after that 3p. 3d2, and then I finish with my highest number of 4s2. So notice I have my 1s together, my 2s together, my 3s together, and I finish with 4. Yes, it is not the way that it filled. I always start off by writing it the way that it fills, and then I go back and I group everything together. Let's look at nickel. Put your finger on nickel on the periodic table. It is in that 4th row, so I got to get past 4s2. And if I look in the D's, which is 3D, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8. It's the 8th one. So I would write 4s2, 3d8. But when I write it out, we keep our numbers together. So here's my 1s, there's my 2s, there's my 3s. All I'm doing is flip-flopping these two to keep my 3s, S, P, D together. And I finish with that 4s2. Here are orbital box diagrams for calcium through zinc. So we know calcium, there's none in the D's. We just say 4s2. And then SC, we've got our 4s2, 3d1. Titanium, D2. Vanadium is 3. Now, notice that this guy has a little asterisk, and so does copper. They don't quite follow the rules. Look over here. They didn't fill up 4s2 before jumping over to the D's. Same with copper. You don't need to memorize that because those are anomalies. But notice that it still will add up to the correct number, because instead of going from 3 to 4, it went from 3 to 5, and then it lost one there. So it still is just one more electron. Same with down there with the copper. Pause here. I have 10 your turns. I'm going to go through these kind of fast, but what I would like for you to do is to pause and check your answers. And that wraps up section 3. We are moving on to section 4 next.